So we will first start with the overall challenge summary. So we organized the OOD-CV challenge and our workshop. And the motivation for our challenge is that typically computer vision algorithms are tested on ID test data. That is, the training data is very similar to the test data as shown in the figure. But their performance of these deep learning models in the real world scenarios can degrade significantly. For example, on these images with different shape or 3D pose, texture, context, weather, and maybe novel occlusions, deep learning models typically perform bad on these examples. So we collect this data set that is presenting also at ECCV. We collect this data set to evaluate actually 3 tasks, but 1 task is canceled due to a mistake. So 2 tasks, image classification and object detection as challenge tracks at the workshop. So how do we collect these images? We search the images from the internet using some search keywords like the Batman's automobile for some motorbikes that have the novel texture that is a Batman texture, and we label them with bounding boxes and classes so that it enables testing for classification and detection. So for evaluating the model, we want to specifically measure the model's robustness with respect to OOD nuance factor. That means we must ensure that the testing is really OOD, not like use a lot of data and the OOD testing is somehow ID testing. So to measure this robustness with respect to OOD, we pose 2 constraints. First is a data constraint. Only the image at 1K data and the provided training data can be used to train the model for submission. And also we constrain the accuracy on an ID test set. That is to ensure that our participants not just train a very large model on all the data or use very strong augmentations to get a better performance. Because empirically we see that the OOD performance actually also goes up when you have a higher ID performance. So we want to ensure that people are developing algorithms that are truly improving the OOD performance, not just improving array performance. So how do we pose this accuracy constraint? We define the threshold as the performance on the ID test side as the following number. This number is obtained by we train a baseline model 5 times and compute the mean and standard deviation of the model on the ID test set. Then we take the mean at the S3 standard deviations on the mean as the top threshold for the ID performance. So our challenge kick off at August the 1st, and by the end of the challenge, we have received a lot of submissions and a lot of teams. So for classification, we have 88 teams participating. For detection, we have 59. And for the number of submissions made by those teams, we have over 600 submissions for classification and over 400 submissions for detection. So now I'm gonna announce the winners for classification track. The prize money are sponsored by Future Fund Granting Program, and the first place with a $2,000 prize goes to 一路郭、星月石、吴杰成、魏杰成、施彩阳、狄谢、施良普、岳廷壮from Hackvision Research Institute, Peking University, and Zhejiang University. And the second place with $1,000 in prize money goes to Junyu 柯达鲁、浩长、莫寒静、小华旗、李文章、志宏伟、叶瑜、方高 from the University of Science and Technology of China. And the third place goes to苑鹏图、凯吴、博胜章、永流 from Tongji University. And also a fourth place goes to 门心林、玉记、盛开王 from the Technical University of Denmark, University of Chinese Academy and Science, and Sichuan University. And for the winners of the detection track, the first place goes to 韦照、冰冰晨、魏杰晨、施蔡阳、地谢、施良普、岳廷壮 also from Hikvision Research Institute and Zhejiang University. And second place goes to Tuhong Kim, Yosef, Shora Drakhmotov, Abdullah Namazov, Kihua Li, Adna Metap. Sorry, I tried to pronounce everyone's name, but it may be incorrect. Sorry. From National Institute of Technology, Delta X Corporation, and DP World. Third place goes to Junyu, 柯达路、浩长、莫航静、小华旗、李文章、志宏伟、叶瑜、方高 from the University of Science and Technology of China. And first place goes to 子宁晨、天一王 from Beijing University of Post and Telecommunications. Apart from the prize money, the winners will also be invited to submit to a special issue in ECCV. Is a special issue in robust vision. Okay, so a TLDR on what works for the challenge. So basically, we'll look through all the challenge submissions. The most effective approach for argumenting the training data is to use some weakly supervised segmentation to crop out the from foreground objects and apply it on some novel context, or just crop out some other class object and apply it as a novel occlusion. So basically, this method works very well, and I think the top one summation of both classification, detection submissions use this technique. And another thing is weather simulation is to use some algorithm to manually corrupt the image with some weather variations. And second, image mixture-based data augmentations. That includes the use of cut mix or mix-up. And also large backbone models are used for every team. Every team use some large backbone models for their submission. And ensembles also works well for our challenge. And other things like test time augmentation, like 5-crop, 10-crop are used. And also notably the pseudo labeling on the test data also works well for our challenge. One interesting finding is that actually no method consistently wins on all nuances. As shown in this image, the numbers in the bracket are the rankings of the performance on each nuances. For example, our first place on the classification track actually has the lower performance in texture nuances compared to other submissions. And for our second place submission on the classification track, they achieve a very good performance across all nuances, but for the texture nuances, they only rank the 13. And same goes for third place. And also for detection, the same thing happens, that no team actually wins on all the nuances. So that's our challenge summary, and we want to acknowledge future from regraining program for providing the prize money, and for AIT for providing the data annotation. Thanks. That's the summary of the challenge we have in our workshop. And next, we will show the presentation videos from the classification track, from the winners of classification track and detection track. First, we will go to the classification track winners, play the videos, and followed by a 5-minute question and answering. So, okay.
Hello everyone, I'm Yilu Guo from Hydration Research Institute. I'm glad to share our solution for the challenge. As we all know, deep learning models are developed under the implicit assumption that the training and testing data are independently and identically distributed. The model usually performs badly on the auto-distribution data, and the challenge decides different OOD nuisance factors, such as weather, occlusion, shape, pose, context, and texture. And its aim is enhancing model robustness to the OOD nuisance factors. To address the problem, we analyze the data firstly. In the weather nuisance, the objects are usually under variance weathers. In the context one, the objects have uncommon backgrounds. As for the shape is often strange, and there are different textures and colors and unusual pose for texture nuisance and pose nuisance, respectively. Some masked objects are pasted to the images for occlusion nuisance. We design some augmentations against different nuisance. Specifically, for weather, we follow ImageNet-C to implement image transformation simulating calmer weather conditions, including rain, snow, fog, and sunshine. For other nuisance, we apply corresponding transformation and design a segmentation-based augmentation strategy to transform the objects better. It's an overview of our approach. We choose Swing Transformer V2 as our base model. We train model by SGD and cosine decaying learning rate, and label smoothing is used. Some data augmentation is designed to simulate the nuisance, and common data augmentation like AutoAug and CutMix are used. We choose test time training as a noise label learning problem. During testing, we use time-chrome inference and ensemble several models. Let's see some more details. We propose a novel mask-level copy-paste data augmentation strategy against different nuisance mainly based on weakly supervised semantic segmentation. Specifically, we train an image-level supervised semantic segmentation model on the Rubin training dataset by MCT former. After getting the segment masks, we can apply random affine transformation and color transformation to augment the foreground objects, and then paste the foreground objects onto task unrelated image set from ImageNet dataset. In addition, we train another image-level supervised segmentation model on the image from task unrelated classes in the ImageNet dataset. Then we randomly passed the task unrelated foreground objects onto the task-related image to imitate object occlusion. By stacking with other data augmentation strategies, include AutoAug, CutMix, and rule-based weather simulation methods, we can get a per-train model with a strong domain generalization ability as our strong baseline. So test time training can be regarded as a source-free unsupervised domain adaptation, as a strong baseline can get a not bad performance on the test data. Regarding the strong baseline as a noisy annotator on the unlabeled test set, the test time training procedure can be considered as an instance of noise label learning. To this end, divide mix is modified to conduct the test time noise label learning. Specifically, two discrepant models that trained by different random seeds or hyperparameters are used as the initial model. Every epoch, a model divides the noisy training set into a label subset and an unlabeled subset, based on the assumption that the clean samples have lower losses. After obtaining the labeled subset and the unlabeled subset, divide mix follows the semi-supervised method mix-match to mix up the labeled samples and the unlabeled samples, and calculate the cross-entropy loss and mean square error loss on them specifically. Especially, we use weak augmented views for getting refined labels and use strong augmented views for training. During divide mix, the performance might degenerate after a amount of epochs, so we update noisy pseudo labels every 3 epochs, which can correct the noise label in time while avoiding overfitting the noise label, resulting in a better performance. During testing, the time crop inference are utilized, which crops the given image into 4 corners and the central crops plus their fleet vision. We ensemble several models trained by different hyperparameters, while a entropy-guided model adaptive ensemble strategy. Specifically, we choose a model as an anchor model. For one image, we choose the result if the entropy of the prediction result from the anchor model is small enough. Otherwise, we use the averaging results from several models. In this way, the inference time can be reduced. There are some experiments. We compare different model architectures and capacity. From the table and the curve, we can see the transformer usually performs better than CNN, and the bigger the model, the better the performance, while transformer with similar capacity performs similarly. Considering speed and resource consumption, we choose 3 transformer V2 base as our base model. There are some results with different methods on phase 1. The single nuisance simulation can enhance the robustness to the corresponding nuisance but may damage other performance. When using them together, we can get a stable improvement. Divide mix without label periodically updating is unstable and might degenerate during test time training. It's a curve for the performance. As we can see, the used method improved the performance incrementally, and the test time noise label learning enhanced the performance significantly. On the phase 2, we train several models by different parameters, like different threshold for divide mix, different random seed, and different epochs. After ensemble them by entropy guiding, we can get a performance over 1887 on the phase 2 and get the first place. That's all. Thanks for your listening.
Okay. Is a team here? Hello?
Yeah, I'm here.
Okay. So thanks for the presentation. Does anyone have any questions for the team?
I can ask a question. So in the final results, it seemed that for the texture nuisance, the model achieves, I think, quite a low performance still, like 77 or so performance. This is kind of in stark contrast to some of the other nuisance variables. So can you comment on why this is still the lowest value? And if this could be resolved by additional data augmentation? Or what's the solution to this problem? Can you hear me?
Yeah, I can hear you.
Sorry, I haven't catch it.
So when you go back to your slides in the results for the texture, like the texture variation, your model is not does not perform so well. As opposed, for example, to pose variation, where it performs better, or context variation. So what is special about the texture variation that makes it so difficult?
The texture.
Like if you could pull up your slides again if you want, like with the numbers, with your final result on the phase 2. Yeah, so when you go to texture, it has like 77.5, the model ensemble performance. But for occlusion, it's 97. So for texture, it's pretty low compared to other variances.
Yeah, maybe the texture on phase 2 is more difficult than the texture on phase 1. We have designed some more challenge texture augmentation, but it didn't make sense.
Interesting. So it seems like texture is still an open problem, whereas maybe occlusion is not so much.
Oh, actually, the third place on the leaderboard has 87 performance on the texture, so that's 10% higher than your solution. So,
that's interesting.